Simon's algorithm. Let's go with this. I find this quite interesting. I think it's definitely helping me to put get a bit of more context in terms of how to use quantum computing to solve certain problems. And despite the fact that it's maybe not exactly what I want to end up exploring at the end of the day, I think that's um, definitely interesting. So let's take a look at Simon's algorithm. Simon's algorithm was the first quantum algorithm to show an exponential speedup versus the best classical algorithm in solving a specific problem. It's inspired by this inspired the discrete Fourier transform, the quantum algorithm of it. Okay, let's see. Okay, so it's sort of one of the things that then ended up inspiring Shor's factoring algorithm, which is, I think it's going to be a difficult one to sort of break down. But let's aim at doing that somewhere in the future. Simon's algorithm solves the following problem: given a function like that, which takes an n-bit string as input and outputs another n-bit string and has some secret structure, and such that given two different inputs x and y, fx equals fy if and only if y equals x plus s module 2. Okay, classically, if the given algorithm picks inputs at random, it will learn when fx I and fxj, so when they are equal, so that okay, so this stands for bitwise addition modulo 2 to the power of n. No, 2, sorry, that's just bitwise addition modulo 2. Each pair determines a bit of s, therefore we need to find n pairs to discover the value of s. It can be shown that okay, I haven't really understood that. The quantum algorithm allows us to find s in approximately n calls to the function f due to the periodicity in the problem. It serves as a natural precursor to Shor's algorithm. So let's try to reread that, which is full of just kind of formally described, but maybe I can just read through the lines in a different way. So it's a function that takes so that I understand. It's a function that takes a string of bits with length n and outputs another string of bits with size n. So, and the idea here is that it has some kind of secret structure, right? Which is also from the same domain, right? So it's also an n bit of and a string of bits of length n. And that it's not. I assume that means that it's not all zeros. Okay, but what is the secret structure S? Okay, so such that given two different inputs x and y, the fx equals fy only. So okay, I what I guess this is saying is that secret. Okay, so what I guess this is saying is that it's a function that repeats itself. It repeats itself, right? So it outputs the same value for two different inputs. Periodically, right? That's why the mod is being used, right? So if and only if y equals x plus s mod 2. I don't quite understand that, but that basically makes it. So what they're basically saying is it repeats regularly. So and the idea here is to try to figure out, I guess, what's that periodicity. periodicity. Picks up and inputs at random. It will learn when f, so that where this symbol stands for bitwise addition, modulo 2. Each pair determines a bit of, yeah, I think that's what it means. The quantum algorithm allows us to find these in n calls to the function f. Okay, so the quantum circuit for Simon's algorithm. The quantum circuit that implements Simon's algorithm is shown below. So let's try to understand. So basically, we've got here a bunch of qubits. It seems like these are sort of two groups. And here we are applying, I understand, Haramarts to all of them. Then there's the sort of QF, like we also have seen in the Deutsch user algorithm, that applies to all of them. Then Hadamard again, and then we're measuring. I don't know what those qubits down here are used for. So the QF acts on two quantum registers as. So that's QF. So QF basically what it does is I guess. Okay, I know what it means. I know. So basically, what this is saying is that those. So this here, what we have here is the input, and so QF basically what it does is it applies the function. It's not that it applies the function, but it basically kind of applies the function, right? So by taking x and then applying the value of fx, on that. Not so sure that I'm getting this correctly. Because it would make more sense that this is the input. No, those are zeros. Okay, let's see. Because I'm kind of sensing again. So basically here we have the Hadamard is going to be applied. So essentially, we're going to have a superposition of all the possible combinations, right? And then we want to apply that function to all the possible combinations at once, conceptually. So the algorithm involves the two following steps. The two n-qubit input registers are initialized to the 0 state. Okay, so these are two different registers, and they're all initialized to an n-qubit input. Okay, to 0. Apply Hadamard on the first register. Okay, so it's just a bunch of stuff in here, but basically that's what it basically means. So that just that just means that you end up basically with a to all possible sort of an equal superposition. So this is just the compressed notation. We make a query QF. We measure the second register. A certain value of fx will be observed because of the setting of the problem. The observed value fx could correspond to two possible inputs, x and y. Therefore, the first register becomes... Ooh, okay. Where we omitted the second register since it has been measured. Apply Hadamard on the first, omitted second register since it has been measured. Apply Hadamard on the first register. measuring the first register will give an output like that, which means a string Z whose inner product with S will be measured. This repeating the algorithm n times, one will be able to obtain n different values of Z, and the following system of equation can be written, from which S can be determined, for example, by Gaussian elimination. In this particular problem, the quantum algorithm performs exponentially fewer steps than the classical one. Once again, it might be difficult to envision an application of this algorithm, although it inspired the most famous algorithm created by Shor. But it represents the first proof that there can be an exponential speedup in solving a specific problem by using a quantum computer rather than a classical one. I mean, let's take a look at an example, okay? Maybe that's going to make it clear. Because... Let's see the example of Simon's algorithm for 2 qubits. We take the secret string 1, 1, so that fx equals fy if y equals x plus s. So that's a bitwise plus mod 2, model 2. Blah. The state of the qubit register evolves in the following way. So this is 1, and this is another register. So okay. So the 2 qubit input registers are initialized to the 0 state. Correct. We apply the Hadamard on the first register, so we obtain that. Correct. So basically here is like, so that's what you get because of the first register, and that's what you have in the other one. So it's sort of expressing your full state, yeah. For the string S11, S11, the query function can be implemented as the following. Yeah, so you see here again, of course, for this to work, you have to implement that, right? So you have to know the function. So it's kind of like you're trying to prove something, but you gotta implement that before. That's why I think those algorithms try to prove an interesting point, but they lack a bit of applicability in that sense, right? So you've got to implement that. So you've got to know the function and hard code it in the circuit. So okay, so and this is implemented this way. So basically, so what this is, and this is what you end up with. So what this is doing, what this is doing, right, is what is happening here. So this is obviously, this step here is obviously the function, right? Because basically what the Q function, so what the problem says the QF does is here is basically it takes that, it applies the value. So is it adding? Is it doing like an addition? Or what is it doing? So what this is doing is it's a control knot on this, and then a control knot on this and that, right? So basically what this would do is if you would have 0 0, right? So if you would have, let me change colors. So if you would have 0 and 0 0 1 1 0 1 1, so 0 0, then you would, so and here we're talking about the first two qubits, so the register 1, and here's the register 2. So in this case, you would end up simply with 0 0, and in the case of 0 1, you would end up with what, with 1 1, with 1 1. If you'd have 1 1 0, you'd end up with 1 1 as well, and if you do 1 1, then you would end up with 0 0. Yeah, because you're applying the control nodes twice. So essentially what this is doing is it possible that this is adding modulo 2? Because that would be 1. Not so sure. I'm not so sure. So we take the secret string being S11, S11. Things I don't know how that function is implemented. It's not clear to me how the function is implemented. So it's basically saying that the QF acts on 2 quantum registers doing that. Yeah, but it's in the function of X, and if I do so what is it doing here? 0 0 0 0 0 0 0 0 1 0 0 1 0 1 0 0 1 0 0 1 0 1 1. Yeah, so you see, I mean, so this is what I just came with, right? I mean, okay, I'm not so sure I understand where does this come from completely, or why this is implemented this way, but I makes sense, right? That we're here. That we measure the second register with 50% probability, we'll see either 0 0 or 1 1. Correct, because we got those. Yeah, exactly. Because we got those values, right? So twice we've got the possibility of 0 0s and twice 1 1. For the sake of the example, let's assume that we see 1 1. Then the state of the system is the following. Why? Well, because we've measured those, then we know that this is not the case, and we know that this is not the case. So that's what we end up with. Then apply the Hadamard on the first register. We apply a Hadamard on the first register, and you end up with that. Okay. Yeah, I mean, you just apply the Hadamard, so. Measuring the first register will give either 0 0 or 1 1 with equal probability. If we see 1 1, then S times 1 1 equals 0. This is one equation, but S has two variables. Therefore, we need to repeat the algorithm other times to have enough equations that will allow us to determine S. Boah. Boo, boo, boo. 0 0 1 1. So define the function. Using these results, we can recover the value of S. First attempt failed. I partially understand. So I understand partially some of the steps, but I don't fully understand the mathematical description of the algorithm or of the problem. Mm. Mm-hmm. Yeah. So, but it seems like, so here it's a bit of a different approach. Instead of exploiting the structure of the problem, we are basically exploiting partial measurements. We're exploiting partial measurements. So what's happening here is that intuitively, right? We are applying something to a function. We're applying something based on a superposition, and then we're measuring that stuff, right? So what we're trying to do is in reality, what we're trying to do is trying to uncover what we have here. So that's why it feels pointless to start with. But let's assume that we want to that's a black box, and we want to uncover what's in here. So what this is doing is it's exploiting it's basically exploiting the fact that when you measure a part of your system, you can infer what else you have. Like you can basically infer what else you have left because of the effects this is having. So by measuring the results, the concept is by measuring, because those things are, and it's sort of entanglement to an extent. Maybe that's exploiting the fact that you're measuring a pair of entangled registers. So when you measure one, you can deduct the information of the other, and I think that's what's happening here. So I'll try to give it another round and maybe try to understand better the formulation from a mathematical perspective. But I think that's what's happening, and actually it's really it's really interesting. It's definitely interesting. I mean, again, its practicality, it's discussable, but that's what the algorithm is doing. It's basically exploiting entanglement and the partial measurement of entangled states of entangled qubit registers to then kind of figure out or try to kind of reverse engineer what was in an original in the original registers. Or what was the transformation applied to those registers? Let's put it this way. Cool, perfect.